Put your answers to the 3 questions about the syllabus in the folder. Today we're going to cover linear equations. Well, not a whole lot on like linear equations as much as rational equations. And rational equations are probably the one area that students have the most difficulty with in terms of solving equations. These things tend to throw you for a loop a little bit. So hopefully we'll, in the sense of, there's sort of an easier approach to doing them, and then there's the really long approach. And I often will have a difficult time trying to convince students of the easier approach. So we'll take a look at those today. Don't forget, Friday Project 1 is due. I noticed a lot of you had a lot of work done already on Project 1 because we started it in class on Friday. Now, if there is a snow day this Wednesday, that would be Class 5, which is in your packet. And Class 5 in your packet is almost totally identical, almost, to Class 5 from Fall 13. So if for some reason we're not here on Wednesday, just follow your lecture notes, follow the class video. I will put Class 5 Fall 13 video into our folder on YouTube. So just follow along. The only difference is there's one problem from fall that I actually put into our Class 6 lecture. In other words, last semester we did just one day on this material, and I've spread it out into 2. So one of the harder problems from Class Fall, or a problem that involves a system of linear equations, I've put into Class 6. Okay, so you should be able to follow right along with everything you see in the lecture notes for Class 5, and then you'll hear a problem that's not even there. You can just ignore it if you want. Okay, so the only change I'll make is if we have a snow day on Wednesday, I will extend the due date for Wednesday's homework. Instead of it being due on Friday, I'll make it due next Monday. Okay, so we'll pick right up with Class 6 on Friday if we have the snow day on Wednesday, because everything will be there. Any questions on that? Any questions on anything so far? Okay, so a lot of you have taken a few minutes. I'd like you to just work on these problems, and in particular, if you haven't had a chance to work on these, why don't you just start right with number B. Number B is the one that would probably give you an issue if you were going to have any issues, okay? Mason? Okay, so take a few minutes to work on B. Okay, so I think I went around and looked. Everybody, I think almost everybody, if not, let me know. Let's just work through this. We're going to use the distributive property here. So we get 3, why isn't this working? 3x plus 6 on the right side, excuse me, left side. Now the only tricky part here that still can be confusing is when we have subtraction, we often forget. Sometimes we do this, we do 10, and then we call that -5 when we multiply the first term, and students will always get this, but it's the second term that causes the difficulty. So it's you can read it as -5 times -4 is plus 20. And the reason you can read it as -5, even though that says subtract 5 and that says subtract 4, is because every single subtraction problem can be changed to adding the opposite. So you could change every subtraction you see in that problem to add the opposite. So that's why we're allowed to say -5 times x and -5 times -4. So even though it says subtract 5, that's really a +5 there you're subtracting. And the reason we're allowed to use that language is because it can be changed to adding -5. So once you finish this, you should get x is 3. Now this is the one difference that many of you will see in this book, is that every time you solve an equation, and we're going to look at 6 trillion equations, different types of equations, I'm exaggerating a little in this class, and some solution sets will be more than one number. So your author wants you to recognize that you're looking at a set of solutions, and in this case you only have one. You notice the braces are already there for you to indicate three sets, so you just throw the 3 in there. All right, and what was the answer for the first one? -1 or something? -4? Okay. All right, so on my math lab, you will see every time you solve an equation, you will see, what is it? Okay, I didn't do it. I thought I saw a negative when I walked around. Okay. So every time on my math lab, when you solve an equation, you're going to see this little empty set here, and your job is to take your solution and put it into the set. Now, if there's more than one solution, remember, you put the smallest number first and the larger number second. Okay. All right. So let's get to the real issues of today. Well, this is I did want to show you how to do this with your graphing calculator. So if we were looking at this same problem right here, and you wanted to see how to solve it with your graphing calculator, you can solve it with your graphing calculator a couple of ways. Either numerically, when we say numerically, we mean we can do it with a table. What we just did was we solved the equation algebraically. So there's 2 other ways to do it. You can do it numerically, or you can do it graphically. So let's take a look how we would solve 1b with our graphing calculator. The first thing you're going to do is you're going to take the expression on the left side of the equation, 3 times the quantity x minus x plus 2, and you're going to throw it in to one of the y equals. Now, we might as well just start with y1. So we go up to y1, and we're going to call that a separate equation. And do it just like you see it, just in case you make a little mistake in your algebra. Put the original expressions on each side of your equation, just like that. Okay, now you take the right-hand side of the equation, this expression, and you put it in exactly like you see it. Okay, don't do any algebra on it in case you make a mistake. So 10, and then your subtraction button's right here. Don't use this minus button, the opposite button here. Minus 5 times the quantity, x minus 4. All right. So there are your 2 expressions that you're trying to set equal. So one way to do this is to use your table feature. Okay, so you use the table and graph features to locate the x value that will make these 2 y's the same. Because what you've just done now is you're saying, when does y1 equal y2? Because you've called this y1 and you've called this y2. So what you're trying to do is you're trying to find the x value that will make y1 equal y2. So you go to your table, you set it up first, and notice what I have here, 1, 2, 3, 4, 5. If we don't know the answer to the equation, like we know the answer, then you would probably just set it at -10 to 10 and take a look at it. So let's see, we got -3 to 1, but our table here for our numeric check starts at 1. So let's start it at 1. We want it to do it automatically now. We're not going to ask it. We're going to want this to generate the answers to y1 and y2 automatically. So now we put on the auto button. So what we're going to look for is if we put a 1 into y1, we should see 1 plus 2 is 3, 3 times 3 is 9. So we should see a 9 right here. If we put a 1 into y2, we'll have -3. So we'll have 10 minus 5 times -3. We'll get a different answer here. So what we're going to do is we're going to look for the place where y1 is equal to y2. We're trying to find the x value that makes these 2 things equal. And maybe we'll be lucky enough that it's one of these 5 answers. So now we hit our table and we go down and we say, okay, not when x is 1, 9 doesn't equal 25, not when x is 2, but you notice right down here, when x is 3, 15 is equal to 15. So if you fill in your table here, you notice that it's not until we get to 3 that the left side of the equation equals the right side of the equation. So that's our solution. 3 is the lucky number. Okay, x equals 3 is the solution. Okay, so we're looking, I want to put that, let's get a picture of that so we can put it right into our notes. So we'll take a picture of this and we'll throw it down here. and get all these things out of the way. There we go. We'll put it right down here. And then we'll just highlight 3, because that's the answer that makes the equation true. Okay, any questions on that? That x equals 3 will make the left side equal to the right side, and therefore it's the solution to the equation. Okay, so that's how we would do it numerically. Graphically, remember now, if you look back here, if I asked you what kind of picture 3 times x plus 2 would make, you could in your mind just say 3x plus 6. What kind of picture would I get if I graphed 3x plus 6? What kind of graph would I get, Mason? So we're going to get, what's the picture look like? What kind of picture would I get? So what is it called? What's the graph called? Linear, right? And linear means you're looking at a line. Okay, and the same is true here. So you're going to be looking at the picture of 2 different lines. They're different because their slopes are different. The slope here will be 3, and the slope here is going to be -5. And they're going to intersect. So the point of intersection is going to be the value of x that makes your first equation have the same y value and your second equation have the same y value. So now we're going to hit zoom 6. We're going to go to our standard window, and we're going to look at the 2 graphs. Okay, so my standard window is not doing a good job here, right? Because I can't see the point of intersection. So this is what I mentioned to you earlier, that sometimes you've got to play around with the window. Now notice, we're not really concerned about the negative values of y, are we? Because the intersection isn't happening down here. But we can see we need to extend our y-axis to look at more positive values. So I'm going to go back to my window, and I'm just going to come down to my y values. I don't really care about negative y values. I'm just going to put a 0 there. And I know I've got to go higher than 10. I'm not sure how high. Well, we know it's 15 from this answer. But I'm going to just make it 20. And then I'm going to regraph it. And now I get to see the point of intersection. So that point right there, the coordinates of that point will give you the x value. In this case, it's going to be 3. That makes both of the y values equal. So to find that point, you go to second calc, and you say, let's find the intersection point. So you go down to there. I'm going to take a picture of that so you have it as well. God bless you. So let's take a picture of that so you know where to go on calc. You go to intersect. Okay, so we're going to put that over here, make it a little bit smaller. Okay, so you remember second calc, intersect. Now let's take a look at what we do when we hit enter. Now this is the really neat part. You don't have to do anything. You don't have to move the cursor so it's close. You don't have to put in those left bounds and right bounds. When you have the intersect command, all you have to do is hit enter, enter, enter 3 times, and it's going to give you the point where it intersects. Enter, enter, enter. And there you go. It intersects at the point x equals 3, 15, which means the point 3, 15, that ordered pair satisfies both of these equations. If you put 3 in here and 15 here, the left side equals the right side. Same with y2. So that point of intersection, the x value is the common solution. So let's take a look at the picture of that down here. So that's the neat thing about the intersection command. Is all you have to do is hit enter 3 times. You couldn't ask for anything easier, really. You don't have to play around with it at all. Okay, so x equals 3 is the solution because it's the x value of that point right there. Okay, so you can see the relationship to both your table and your original equation, both graphically and numerically. Any questions on that? If you're looking at a table, so if I gave you a table like this, suppose I gave you this on your quiz next week on Monday. Suppose I just gave you the table and I didn't have anything highlighted, and I asked you to find the solution for where y1 equals y2, or find the solution for the equations there. You would know that you're looking for the x value that makes the y values equal. Sometimes you can have more than one solution, right? If we have a parabola, say, crossed by a line, right? So you will see something like this next Wednesday, promise, on your test. You will see probably some type of either numerical table like this or a graph that intersects with some kind of question asking about interpreting the meaning. Okay. All right, so let's take a look now at linear equations with fractions in them and try to figure out how we would solve these before we look at the algebraic fractions equations. Suppose I want you to fuss around with this for a few minutes because I want to try to convince you about something. So here's here's a linear equation. It's just a regular old linear equation. The only difference is it has fractions in the denominator. So I want you to start messing around with this, how you would go about solving it. I don't want you to solve the whole thing right now. I just want you to start it and then just take a few minutes and discuss it with your table mates to see if anybody has different approaches to this. I know it's a little scary for some of you when you see those fractions, but we're going to work through that today. Okay, so let's talk about this for a second. Someone want to share how they just started the problem, how they started it. Cassandra? You made all the denominators be the same. And how did you do that? Okay, so what was the common denominator? Okay, so Cassandra decided, because you're all taught, brainwashed to say, anytime I see fractions, I've got to have common denominators, right? So we're brainwashed. So she says, okay, my lowest common denominator that I'm going to try to change each one of these into is 12. And then as we were taught, you say, okay, if I'm going to make an equivalent, Mason? Can I, because I just want to start with where Cassandra is, okay? Then I'll get to you, okay? All right, so x plus 1 divided by 4, and you want to make an equivalent fraction. And if this new denominator has a 3 in it, you'd have to multiply the denominator by 3, so you have to multiply the numerator by 3. So the equivalent fraction would look like this. And did you make this change for every single fraction, Cassandra? Okay, so this one would be multiplied top and bottom by 2. And the next one would be multiplied top and bottom by 4. Okay, so far we're doing okay. Then what would you do, Cassandra? Distributive? Okay, distributive property on the first one. And over here, you can smush those together now, right? Because they have the same denominator. So you have 2 plus 4. Let's do it right now. 8 minus 4x. And then you get 3x plus 3 over 12 equals 10 minus 4x over 12. And a lot of students will get to this point and they don't know what to do. They don't know what to do. There's a couple of approaches. Do you remember what we called two equal fractions the other day when we saw them in class? From any part of your mathematics, two equal fractions? What do you call it? Give me a P. Give me an R. Don't make me look like a fool. Give me an O. Did I spell that right? No. Give me a P. Give me an O. How do you spell proportion? Isn't it P-R-O? It's a proportion, right? And so a proportion, remember, is cross products are equal. So you're thinking, I got to do that? No. Hey, look, if you get this far, because no matter what I show you in a few minutes, and no matter what information Mason gives you as his approach, it's going to be really hard to undo what Cassandra just did. You're going to want to do it this way no matter what I show you. But then you get here and you go, well, look, there's nothing to solve with the denominators. They're already equal. The only thing to solve this equation is to set the two numerators equal. They're gone for right now. There's nothing to do. So to finish this off, you just set the two numerators equal, and you have a baby linear equation to solve. So go ahead and solve it. All right. And if you do that, hopefully I did it right, you get 1. Okay. So try to imagine now that these denominators are no longer single numbers like 4, 2, and 6, but they're things like x squared minus 4, x plus 2. You can get really nasty doing all of this. So I want to show you another approach to solving fractional equations and try to convince you that this is an easier approach. So here we go. We're right back here at the beginning. And I want you to see that even with this approach, you can get to this equation right here. You're going to get to the same equation. Okay, so Mason, now you're on.
So I actually didn't think of the 12 thing. I just said like 4 times 6 is 12. So that would probably be something. If I just multiply the whole equation, sorry, I just turned 4.
Right.
She told me 12.
That's all right. It doesn't matter. You found a multiple, right? And all right, we'll go from there. So what Mason's saying is he looked at the 3 numbers and found a multiple. He looked at it and saw 24. In this particular case with numbers, folks, when they're all constants in the denominator, really doesn't matter because we're pretty at ease with multiplying and dividing numbers. But when these become when they become binomials or trinomials downstairs, we'll want to find the smallest common denominator. So it doesn't matter that he picked 24. But to try to stick with Cassandra's idea, let's find the smallest multiple of 4, 6, and 3. And to find the smallest multiple, you prime factor each denominator. There's the first denominator. The second denominator is going to borrow that 2 and throw in a 3. And then 3 is all by itself. So if you go straight across, 2 times 2 times 3, you get 12. All right, now here's the key. Here's the key. You have an equation now. You're not asked to add and subtract these two things. If you have to add and subtract, was this originally a 2 here? Yeah. If you're asked to, I bet it 3, thank you. How'd I get Excel? Wow, that was tricky. All right, so if you're asked, look, if I cover up the left-hand side of this equation and you're asked to add those two fractions, no choice. You got to convert both of them to a common denominator. But you have a powerful tool available to you, and you don't want to use it half the time. The tool that you have available to you is that you have an equation, and you have the right to add the same quantity to both sides of the equation, subtract, multiply, and divide. As long as that, at least for multiplication and division, it's a non-zero quantity. So I'm going to multiply both sides of this by the whole number 12. And in so doing, I am going to get rid or clear the ugly fractions. Okay, so once you multiply that by 12, I also suggest always put parentheses around any numerator that has more than one term in it. So once you do that, notice your 4 will cancel into the 12 3 times. And so on the left-hand side, I've got my right and left mixed up today for some reason, you get 3 times the quantity x plus 1. Now, if I put a denominator on this, what would the denominator be? If I put a denominator on this right now, what's this? 1, right. I could put the denominator 1. So here's the moral of the story, folks. You are creating common denominators. It's just they're really nice denominators called 1. So you don't even have to put them in. Okay, so let's get rid of that denominator of 1. So there's the left-hand side of the equation. Now what happens on the right? 6 goes into 6 once, and 6 goes into 12 twice, and you have 2 times 1, so you have a 2 sitting there. 3 goes into 3 once, 3 goes into 12 4 times, so you have 4 times 2 minus x. So when you multiply that through, you get exactly the same equation, but without having to deal with fractions. Oops. The same equation that we got right down there. Okay, So you have a very powerful tool. You're still using the same idea of finding the common multiple, but now, instead of putting it in the denominator, which we call LCD because it's placed in the denominator, we just refer to it as LCM. It's a multiple that you're multiplying both sides of the equations by. So you can see no matter which way you choose to do this type of problem, you'll be okay. You'll get to the right answer. One way when we get to algebraic fractions is a heck of a lot less work than the other way. Okay? And again, I've been doing this long enough to know that some of you will still continue to do it this way. And if you're okay with that, that's fine with me, as long as you don't get yourself like involved in really messy stuff. But I think you'll determine this on your own, whatever you feel most comfortable with. Any questions on the idea, the concept about solving these? All right, then now let's take a look at, so this was what I just did. I just had it all laid out for you here. So I just didn't use the chart. So here's a situation that I wanted to talk with you about. These are called rational equations. Again, rational because you're looking at the ratio of two polynomials. Here you got a monomial on the top, a binomial on the bottom, 5 over x plus 2. Here you have a monomial on top, and you actually have a trinomial downstairs. If you multiply this out, oops, it actually is going to be a binomial because it's x squared minus 4. Okay, so these equations now, there's a little more work involved to finding the multiple, but the idea is exactly the same. Everything we did back here, everything we did, including finding the common multiple, is exactly the same. It looks a little different because it's algebra. It's all in terms of x or some variable. So let's take a look at how we would solve a couple of these, and then you're going to spend the rest of your class period working on these. Okay, so the first thing we have to do with these algebraic expressions is we have to make sure this is not, oh, I'll do this if I feel like it, Linda. This is mandatory, this first step, because you want to write down what value of x is not in the domain, because you can go through all this work, come up with an answer, try to put it in my math lab or try to sneak it by me. Without doing this first step, you could have a totally incorrect answer, because sometimes the equation you have will never be true. You'll never find a value of x that makes the left side equal to the right side. So first thing you got to do always when you're looking at solving an equation is to find the values of x that are excluded from the domain. So what value of x here won't be allowed in to the club? 0, right? If x is 0, we get both the first denominators, 2 times 0 and 3 times 0. So 0 is not allowed. So if we go through all the work of solving this equation and we get a 0, then we just say the solution set is empty. And in case you haven't picked up yet, another way to write that the solution set is empty, an empty set, you can use this notation. Okay, that's the empty set. I think you may have seen this on my math lab along the way as an answer. Okay, so the first thing you have to do is find the lowest common multiple. Well, look, folks, if you take the x out of there for a second, what's the smallest common multiple of 2 and 3? 6. Why? Because 2 and 3 are already prime. No work. They can't share anything. They're prime, so you just multiply them and then throw in an x. Okay, if you want to do it visually, you say the first denominator looks like this, and I use colors all the time when I find my lowest common multiple. Okay, 2 times x, that's my first denominator. And to get my second denominator, I'm going to borrow that x, and I'm going to throw a 3 in, which I'm going to use a different color for. And there is my LCM, 2 times 3 times x, 6x. So if you want, you can change every single one of those so you have 6x in the denominator. I'm not going to do that. I'm going to do it what I think is the easier way. So my LCM is 6x. So I'm going to take my original equation, and everything I see in my original equation is going to be bopped over the head by 6x. I'm going to multiply everything by 6x. So if you have, different colored pens or pencils at home, I strongly urge you to use some color. It will help you out in terms of seeing what's going on. Okay, now you have a choice. You could multiply this and say 42x divided by 2x and then reduce it. That's okay. Or you can reduce it before you multiply. So that's what I'm going to choose to do. I see that we have an x in the numerator and an x in the denominator. There's our first foo-foo. That's our first form of 1. And then I see that 6 and 2 share the common factor of 2. So 2 goes into 2 once, 2 goes into 6 3 times. So notice when you put those slashes, everything is multiplication. So what you have on top is 3 times 1 times 7, which gives you 21 over 1, right? 21 over 1. But we don't bother with the 1. We just write 21. That's a lot nicer to look at than everything you've seen so far. It's just the number 21. Okay, we go to the second side. The x's cancel. 3 goes into 3 once, 3 goes into 6 twice. So I have 2 times 5, which is 10. Wait a minute. Whoops. Oh, I just thought I thought I forgot my equal sign when I just a minute ago, and I threw and made the minus. Okay. Minus that. Okay. So far I have no variables on the left side because they've all canceled with that common multiple. So I better probably end up with a variable on the right side or I'm going to be kind of messed up here. Okay, so what do I see here? 6x times 22. Let me see if I can make that multiplication a little easier. 3 goes into 3 once, 3 goes into 6 twice. So now I have that multiplication. 22 times 2 times x is 44x. And now, lo and behold, all you have is a baby linear equation to solve. 11 equals 44x. Divide both sides by 44, and you get 11 over 44, which reduces to 1/4. So on your homework, you put the little 1/4 in the solution set. Okay? So I don't know about you, but that seems to be no problem to do, because I'm not dealing with common denominators and doing all this work and trying to figure out how to solve proportions in the end. I make all my denominators 1 and I get this nice purple equation. So I want you to try this now with part B. Part B. And use your flags if you have any questions. Talk to your table mates, whatever you need help with, just let us know. What two values of x will make these denominators 0? -2 and 2. Now, why did I say two values of x? Because I see two different denominators. When I look at these two denominators, what I see in my head is something like 2 and 3. Because these two denominators are both prime. So when I think of denominators like halves and thirds, 2 and 3 are already prime. The only way to get a multiple, we just went through this, when you have two prime numbers as your denominators, is to simply multiply them together. Notice what the denominator is on the right-hand side of your equation. It's the first denominator times the second. This already is the multiple of these two denominators. So the LCM here is x plus 2 times x minus 2. Now, I saw some of you out there changing each one of these fractions to have this in the denominator, and they were looking like monster equations, okay? And that's fine if you want to do it. I'm not going to do it that way because I don't want to encourage that method, okay? If you have a question about what you did, if you can't come up with the answer that I come up with, I'll be glad to help you out. So the idea here is I'm solving an equation. I can multiply both sides of the equation by a multiple that's not 0. And I know this is not 0 because I've excluded those two numbers from the domain of this solution, of this equation. So I am going to take x plus 2 times x minus 2, and I'm going to put it over 1, and I'm going to multiply it by each of the original pieces of my equation. Now notice, one of the first things I did was put each of my denominators in parentheses, and that just helps you see it as a single factor. Okay, then I'm going to add, I'm going to use my multiple again over 1, and I'm going to multiply it by 3 over x minus 2. And then I'm going to set the whole thing equal to 12 over x plus 2, x minus 2, and that has to be multiplied by the LCM as well, or I've really done a big taboo in mathematics. You've got to multiply both sides by the same quantity. Now, all I do now is find my common factors of 1 because I'm multiplying here. So this is just one big numerator right there. That's just one big numerator, and that's one denominator. So I have an x plus 2 in the denominator and an x plus 2 in the numerator, which leaves me with 5 times x minus 2 over 1. Beautiful. I don't have all those x plus 2, x minus 2's in the denominator. Plus, now what am I left with here? I have an x minus 2 in the denominator and an x minus 2 in the numerator, which leaves me with 3 times x plus 2. And this whole thing is equal to, and look at how beautiful this one turns out, both of these factors cancel with both factors in my multiple, so all I have left on this side is 12. Now, for those of you who didn't use this method, you have denominators for all of these. And you might, as long as your denominators are all the same, you might as well just erase them right off your paper right now because they're not part of your solution. So now you use your distributive property and you solve this baby linear equation. And when you do all your work, wait a minute, what did I do? Did I make a mistake here? 3x plus 6, 5. Oh, 8x, thank you. 8x. So you get 8x equals 16, x equals 2, and you're all set to circle it and say it's your answer. And my math lab is going to say, and you're going to say, what did I do wrong? And you're going to forget that that's the one value, one of the two values x cannot be. Because if you try to go back and check, and you throw a 2 in here, you get 5 over 4. That's kosher. If you put a 2 in here, you get 3 divided by 0. There's no such number. So what this tells you is that even though we have an infinite number of numbers in our real number system, you can't find one number that you can put in for x to make the left-hand side equal to the right-hand side. So you can write no solution for your answer. You can say empty set, or you can use the symbol for empty set. Okay. All right. So I'm going to work this next one with you, and then you're going to have about 20 minutes to work on problems on your own. So most of the time, folks, you're not going to have your denominators factored for you. Part B, there was already one step done. You see this denominator right here, x plus 2x minus 2. That's already been factored for you. What you're going to see, what this will look like in your books will probably be like this. It will start off looking like that, x squared minus 4, and it's your job to factor. That's why I told you P5 was an important section for you to review and do the work for. So you have to factor the second denominator. X is already factored. It's prime. Okay, I can't even figure out my excluded values yet until I factor everything. So the one part of factoring that we always forget is the GCF. And I have all of my 106 students, I tell them that's the only time they can cheat is they can write GCF on the palm of their hand so they don't forget, and you're welcome to do it too. The GCF here, the factor common to both of those is x. So you have x in the first denominator and x times x minus 1 in the second denominator. So you have two different factors here. You have the factor x and you have the factor x minus 1. Those are both prime. We multiply them and that's your LCM. You're all set. That's like 2 times 3 again. So now you can say what you would exclude from the denominator. If you write x equals 0, then that will make my first denominator 0, so that's an excluded value. If you look at this factor, x minus 1, and you put a 1 in there for x, then That will make the denominator 0. 1 squared minus 1 is 0. So those are the two values you can't have. So now I'm going to multiply. First thing I'm going to do is I'm going to rewrite this equation all in factored form like this. And now I'm going to multiply everything by my LCM on both sides. X times x minus 1, x times x minus 1, and x times x minus 1. And you've manipulated this equation so this multiple will always have a common factor with each of those denominators. You've made it work out that way. X's cancel, and you get x minus 1. Both the x and the x plus 1 have common factors with the top, so you're just left with a 1. And this equals 5x times x minus 1. So on the left-hand side, my 1's cancel. I get x, and I get 5x squared minus 5x. This is a different equation. This is a quadratic equation. This is not linear anymore. So now you set one of your sides equal to 0, one side of your equation. So I'm going to take the left-hand side and I'm going to subtract x from both sides. So I get a 0 over here, and I get 5x squared. And when I add those two together, minus 5x and negative 1x gives me minus 6x. Now, just like we had earlier, in order to solve this equation, you want to take this subtraction problem and factor it. And what's on the palm of your hands? What's on the palm of my hands? GCF. So you ask, what's the GCF of 5x squared minus 6x? And what do you get for the GCF? Etc. What's the only thing common to both of these as a factor? X. So the GCF here is x, so you pull that out front. And you have 5x minus 6 equals 0. And now you say, okay, I can figure this out because now I have a multiplication problem equal to 0. So if I set my first factor equal to 0, I'm done. There's nothing to do there. X is 0. If I set my second factor equal to 0, I've got a little bit of work to solve that equation. I add 6 to both sides. And then I take that equation and I divide both sides by 5, and I get x equals 6/5. And most of you are just going to try to circle both of those answers, but I hope you notice that x cannot be 0, so that's not part of your solution set, but 6/5 is your answer. So when you put this into my math lab, you write in 6/5 as the only solution. Okay, so, huh? You can't, huh? Oh, well, just do squigglies. As long as just even go like this, like you're, doodling, and that's fine with me. So as you can see, some of these problems have some work involved, but folks, it's not as much work as your homework you just had where you had to add and subtract fractions. It's a lot less work because you don't have to change everything. So the next thing you have, I'm going to skip this, even though it's a really cute picture from, what is this called, Bridesmaids or something? Yeah, I thought that was a very funny. Okay, so what you have now is you have a worksheet called Modeling Resistance. You're going to have some fractional equations with applications, and work on this at your seats. And any questions at all, just raise your hand and I'll be glad to help you out.